We don't need a transcript, thanks. All right. All right, are you seeing you're seeing a cap area net, folks online? Mm-hmm. Excellent. All right, so yeah, we're caparea.net. We do have a YouTube channel, so we post some, but not all, but many of our presentations to this YouTube channel. So I always, when I'm online, I'm always like, I don't know who I should be talking to the screen or talking to the in-person people. All right. Yeah, so if you were here last month, we had dumb mistakes I've made with relation to databases. Kevin Griffin came up, and that was an awesome presentation, and he requested that we not record it. So there is no recording available of that, which actually made it kind of fun, I thought, because, you know, he was like, okay, now you tell me about your dumb mistakes, and we all got to be honest about it and not share that for the world to know. So that was kind of fun. We meet the first Tuesday of every month now. That is, yeah, we're a little off schedule this month because I was on vacation. Oh, there's stuff that I forgot to take out. And if I actually presented this, then we wouldn't see sponsors that aren't sponsors anymore. But Inferno Red is an awesome sponsor. We want to thank you very much, Scott and Inferno Red, for making this space available to us and for making the pizza available to us. So thank you very much to a wonderful small company that's here in the DC area, but also everywhere, and 100% work from home, and a just, you know, great all-around company. I don't know, anything you want to say?
No, that's great. And Lee is one of our longest tenured best developers, and we're glad that that we are involved with Cap Area and continue to do so.
So on August 5th is our next meeting. I hope you all will have the opportunity to come out. This is going to be an architecture talk. And so, you know, we try to mix things up, do different types of topics. So we've got kind of an AI theme tonight with vector databases, and then we'll do more of an architecture one. And then I've got a new talk that I'm working on, Code Faster, Ship Sooner, Quality First, .NET Development with GitHub Copilot Agent Mode. And that's about full. But yeah, I've been fiddling around a lot with agent mode and having a lot of fun with it. And I am finding it to be pretty cool. This talk is going to be evolving fast, just like this technology is. So it'll be interesting. You know, I'll be interested in getting everybody else's feedback, how everyone else is using Copilot. So that I tentatively scheduled for October 7th. We don't have a September speaker just yet. I suppose I could maybe move mine up. We'll see. So yeah, the Brandon Atkinson post, he's coming up from Richmond for the hexagonal screaming architectures in .NET. So looking forward to having him there for that. Do we have any announcements? I'm going to actually give you two announcements real quick. One, tech events. Nova Code Camp is officially coming back. It is Saturday, October 18th, and it's going to be in the Microsoft building in Reston. And we are just in the beginning stages of getting this thing set up, but we do have a date, we've got a location, and it's confirmed. So please save the date. It's going to be great. And Guy, that applies to you too. If you are interested in coming out to Nova Code Camp, it's going to be, I can't remember if you've come to this in the past, but it's going to be a good time.
I did it virtually during the pandemic, but I haven't done it in person.
Cool. Well, let's talk afterwards. Maybe we can figure something out. Does anyone have any announcements? Any positions to fill? Anyone seeking work? Any other tech events, blog posts, fun projects? All right. Cool. If you're here in person, you could do name tags, but I guess we don't have a huge group just yet. So if you are interested in getting a permanent name tag, put your name on a list. I put a sign-up name, and I thought it'd be fun. I've got a little extra wood, and I've got a laser cutter, so why not? I can just whip out a couple. If you're attending virtually, please keep your camera off and your mic off by default. Please use reactions. Please use the chat. The reactions are especially important because presenters do, they do appreciate feedback as much as possible. Keep it family friendly, polite, and respectful. And without further ado, I'm so excited to have Guy Royse, who is speaks everywhere. You see him at all the conferences. And we're so honored that he chose to speak with us tonight. So yeah, let's hand it over to Guy. Thank you for coming out, Guy.
Absolutely happy to do it. I mean, I don't even have to leave I don't even have to leave the comfort of my office. Although to be fair, I did kind of get my fill of virtual conferences during the pandemic. But I still do them occasionally, and certainly I thought this would be good. And I may see about trying to come down for Nova Code Camp this year. It's in October, and I'll be available. And it's so like a 6-hour drive for me maybe, and so I'd probably just drive. So that makes the logistics a lot easier. So anyhow, let's go ahead and get this party started. So I've got a talk here. It's called, and I haven't done this talk in about a month and a half, so I may be a little rusty. And I didn't rehearse it today, but I did make sure my demo works. I got a new computer, and it's like, okay, well, is everything going to work? And everything should work. Worked this morning. The only thing I'm iffy about is, will I be able to access my camera right here that I'm using to talk to you all, and use it to capture an image for my my demo at the end. So we'll find that out together. Worst case, I'll have to turn my camera off and do something. So welcome to my talk. Modern problems require modern solutions. Finding your meme twin with embeddings and vector databases. As you already know, I'm Guy Royse. I'm a developer advocate at Redis. Here's a bunch of social media stuff on here. I often will joke that there's 3 things on here that matter. One of them will matter to you, the audience. One of them matters to me, the human, and one of them matters to my boss. And the thing that matters to my boss is that Redis logo right there. And he would like you to know that Redis is more than just a cache. You've probably used Redis or heard of Redis. It's kind of everywhere. If you go to Docker Hub, we have billions of downloads. It's into McDonald's hamburger numbers. And so it's a very popular tool, but it's primarily used as a cache. It's a little bit typecast. And he would like you to know that Redis is more than that. It can be all sorts of interesting things. It can be a primary database. It's got more than just strings. You can store all kinds of interesting data structures in it. And it can be a vector database. And so that's our topic today. So that's the thing that matters to my boss. And honestly, it matters to me a little bit because I have options and I would really love for them to turn into a big pile of money someday. So, and then I'm, if it's a big enough pile of money, I'm close enough for retirement. I might just be done and I can just go talk about things that tickle my fancy as opposed to things that I get paid to talk about. So that's the part that matters to my boss.
You sharing? Did you mean to be sharing your screen?
Yes, I do. Am I not sharing my screen?
I don't think so. Maybe not yet.
Okay,
or maybe
well, let's fix that. I think yeah, I'm not sharing my screen. Okay, let's go
here. It from you. I'm about to give it back. It was very rude. I apologize.
Change your view. Share that screen. There we go. It's sharing now. It's sharing now. And let's look for the layout. We'll go side by side, and there I am. There we go. That probably looks
you're looking
gorgeous.
At yourself. That's fantastic.
So this is the part that matters to my boss. That was the joke that I totally ruined by not sharing my screen. And the part that matters to me is all these social media links here. So I'm on Blue Sky, I'm on X, I'm on LinkedIn, all those things. Give me a follow on whatever platform you desire, and that just makes me feel like a good human being because people like me enough to follow me. And then the thing that matters to you is the GitHub link right here, github.com/Guy Royse. Because all my code and demos and all that stuff are out there, including these slides and the code I'm going to show you tonight. So it's all out there in GitHub for you to download and run, and Docker compose up, and you can find your meme twin as well. So an important caveat that I always like to go into when I do these talks that are based on any kind of it used to be called machine learning, and then it was called data science, and now it's called artificial intelligence. But it is all kind of math at scale to make computers do things that they were traditionally hard at doing. This sort of stuff is that I am not a data scientist. I'm a software engineer, probably like everyone else in the audience. I've been writing software for decades, and I'm not trained in data science. And so what this means is that my observations are going to be true So there's two things here. I like to say that I'm a fan of data science and all of these data science things. This is what I'm showing you tonight. It really isn't data science, but data science build it. But I'm a fan of these tools and these techniques, and but I'm not an expert. So I get excited, I go out and learn, and I share, but I'm not an expert on these things. I'm just someone who uses them. I'm a user of them, just like you. And there's actually there's an important thing with all of this stuff, and it's sort of like we need a level of understanding akin to that of a mechanic. So you've got a mechanic, and you go to the mechanic, and he understands how the engine in your car works. And he understands it well enough that he can fix it and repair it and understands the basic workings of it and probably understands the workings of it really intimately. However, he doesn't understand it, or she doesn't understand it to the level that a mechanical engineer does. A mechanical engineer who designs an engine knows this. Okay, so I need to design it to use this specific weight of oil because of these, fluid viscosity breakdowns, and this level, this type of steel is needed because of the, the thermal blah blah, a bunch of stuff that I'm just making this up. I don't actually know what I'm talking about. But we are mechanics when it comes to these tools, these AI tools that we're using to create embeddings and to use LLMs and using these tools. The engineers have built them for us, and we are the mechanics who are working on them and using them to build applications. And so I want everyone here, the goal here is for you to get that mechanics understanding of how these things work, not necessarily to understand how it works at a fundamental level. What this means is that I'm going to say things that will be true enough for us to work with them. But if someone in the room is a data scientist, they may say, well, I'm actually, and point out how I'm a little bit wrong. That's fine. I'm okay with being a little bit wrong. So just a quick show of hands, actually. Is anyone out in the audience a data scientist? I can't really, I don't see any hands going up, and no one's raising their hands virtually. No hands. Excellent. So what I meant to say is actually I am something of a data scientist myself. So you should just believe everything that I say and go with that. So, but yeah. So jokes aside, here's another joke. Our agenda tonight is to cover 4 topics. Is 4 agenda items a lot? Well, it depends on the context. For a talk at a conference? No. Or a meetup. For a talk with your boss? Absolutely. The 4 topics we're going to cover tonight are what the heck is an embedding? Getting your head around what these embeddings are and represent and how you can use them, and specifically how you can use them. So that's the second item. So what's an embedding? How do you use embeddings? How can you make embeddings, both just using code and tooling and stuff like that, but also an underlying understanding of how the embeddings work if you wanted to build your own embedding models, which I don't recommend doing for production, but I totally recommend doing for learning. And then last but not least, we have a code and demo to show you that this is a real thing. So we're going to start off with learning about what an embedding is here. Now, am I the only one around here that knows what an embedding is? Perhaps. I think to understand what an embedding is that, by the way, I love giving this talk in Europe because I used Adobe Photoshop to AI fill in the rest of these images, because these are like a lot of square, small images at low resolution. And so it figured out it was in a bowling alley and all that kind of stuff. But then it saw a gun here, right there, and decided it needed another gun in the background. And I go to Europe and everyone like, isn't that just how bowling alleys work in America? But it just makes me laugh that the AI decided it needed more guns. But in order to understand what an embedding is, I want to kind of talk about first about the data, what data is, what the 2 types of data. There are fundamentally 2 types of data. Structured data. This is stuff that we've been working with our entire careers. It's anything that will go after a where clause. If you can filter it with a SQL statement, then it's structured data. It's JSON. It's keys and Redis. It's numbers. It's strings. It's floats. It's integers. It's maybe more complex things like locations and things like that that have a schema, and that you can use. It's the stuff that we've been working with our entire careers. It's almost everything I've done up until the last few years. That's structured data. Structured data is you work with it using structured queries like SQL or JSON path or something like that. And then there's unstructured data. And this is harder for computers to work with up until recently. It's things like text, prose. So you've got like natural language text, a product description as opposed to a product ID. Or images, is this picture, what is in this picture? Is this picture similar to another picture? Or audio, which would be, it's in some ways audio is also natural language, but it's voice instead of text, or maybe it's bird songs and you're trying to match those things. This data is unstructured. It's hard for computers to work with, but it's really easy for humans to look at. You can look at this, you can read a text and say, yeah, it mentions fast food restaurants because it has Taco Bell, Kentucky Fried Chicken, and McDonald's in it. Or you can look at an image and say that has a cat in it, whereas having software do that is harder. But we're going to talk about how you can do that using embeddings, and that's what we're going to talk about tonight. Structured data is something that we've mastered. We understand structured data really well. We've been using it, like I said, our entire careers. If you've used a relational database, you've used structured data. If you've used a dictionary, you've used structured data. And structured data is easy to manage. What you do is you just put all of your company's data in SQLite, and then your problem's solved. Because SQLite will scale really well, right? If SQLite is perhaps not enough for you, you can always store all your company's data in Access. How many people have had projects early in their career where, yeah, we got this Access database and it grew up and it's, and now we need to put a VB6 application around it? I did that. So you store them all in SQLite, store them all in Access, and if that's not good enough, then you can do what all the big boys do, and that is store your structured data in Excel. So we know how to handle structured data. We've been doing it for years. Unstructured data, though, is a little trickier. Storing it is fairly easy because ultimately it's just blobs of data, and so you can put it in all sorts of fields. And storing it, but querying on it, that's hard. So how can you query on unstructured data? Well, you need to turn it into an embedding. An embedding is a numeric representation of the meaning in that data. So if you've got, say, a piece of text or an image, here we've got a meme. They got the text and the image separately. Don't need to debug your code if it doesn't compile. This is why I'm a JavaScript developer. And so you can take that text and you can run it through a series of processes, for the final process being a neural network, an AI model that turns that text into an embedding. And so here we might want to summarize that text. Maybe it's really long and we need to make it smaller to fit the context window of the model that is going to use it. And then that model is going to take it and tokenize it and get all the words in it and turn them into tokens. These are just numeric representations of all the various, well, basically words, but not really, because a token can be a word, but decompiled. It probably will break up into 3 tokens: D, compile, and ED. And so you've got this thing happening where tokens are sort of grammatically significant things. They could be words, parts of words, punctuation, and things like that. And so you tokenize it. Those tokens get turned into numbers. Those numbers actually get then turned into embeddings using an embedding model. And the embedding, what it does is it spits out location or a series of numbers. It's literally an array. And so you have some model. It takes, its purpose in life is to take text, natural language text, and turn it into a pile of numbers. Usually, I think like 512 is not an unusual numbers. And so these are fairly small. I mean, you could feed War and Peace into an embedding model and then distill it down into a few hundred numbers. And that will encode the semantics, the meaning that is in War and Peace. Similarly, you can do things with images. You can take an image and you can transform it. And so you scale it so that it's square and it's the right dimensions. And then you can pass those into various convolutions in a neural network. And then at the end of a series of convolutions, you will end up with an embedding layer, and you can create an embedding. And this, again, is a neural network that takes an image and turns it into a pile of numbers. Now, these numbers are, I mean, from a developer's point of view, I get a pile of numbers and I can just, it's literally an array. So when I do this in JavaScript, it is an array of 16-bit floating point numbers. It's that simple. But this array means something. It means something to the model. And well, you can think of them as sort of like levels or sliders that determine attributes that the model has looked at the image or the text and associated with it. And so we're going to play with images, and we're going to pretend that we have an embedding of two values. They're not really two. There's usually hundreds of them. And we're going to pretend like elderly and alcoholic are things. Whoops. There we go. My mouse went to sleep. Elderly and alcoholic are the two axes that the model has identified. In reality, the values those numbers represent are more complex than that. But this is simple enough to get a rough understanding of it. And so you can take an image, and we get two numbers here. We get a number from -1 to +1 or 0 to 1. It depends on the model. And here we're measuring how elderly the individual in that picture is and how alcoholic that the picture is. And so here we have Leonardo DiCaprio right here, and he's got a coupe glass, so he's clearly got a cocktail. But he's not particularly old, so it's the elderly value is kind of low, and the alcoholic value is kind of high because there's something in the image that suggests that he's alcoholic. And so if we had a simple embedding that had two attributes, and one of them the model decided was elderly and the other was alcoholic, then this is numbers you might see. Conversely, other images might get other values. So here we have Grandma finds the internet, or Grandma discovers the internet. This is one of my favorite memes, just because I don't know, you can just put things on it that are so inappropriate that I'm not going to talk about them here. But it's a really funny meme. And Grandma here is clearly very, very elderly. But there's nothing in here to suggest that grandma is alcoholic. And so that score is very low. So you can think of these as sort of like rankings of how elderly or how alcoholic, or, if you had pictures of cats, whether there's a cat in there or not, how the catness of it, and, or the dogness of an image. And so you can think of these as scores. And then what you can do is you can take the scores, these piles of numbers, for different images. Here we have Success Kid, the most interesting man in the world, and Mocking SpongeBob. We've ran them through this process. We've ran them through the transformation and the convolutions and the embedding to get a series of numbers that describes what Success Kid is, and the meaning or the semantics in the most interesting man in the world and in Mocking SpongeBob. And we get our piles of numbers here. And then we can then compare them with another image, and we get a pile of numbers for that. And then what we can do is we can compare numbers that are similar, are going to map to similar things. And so in this particular case, you've got a middle-aged white guy. And so we've got a middle-aged white guy. And so these two things would be more similar than perhaps these two or these two all to each other. And so you're measuring how similar these things are by looking at how similar the numbers are. And the way we do this is actually fairly intuitive, because what you need to realize is that these values, and I use two of them for a reason, can be thought of as a point in space or a vector shooting off from origin. And so here we have in the top left, I take that back. This is my favorite meme. You got the little drunk baby with the really big glass of beer here. He is clearly not elderly. He's young. But it suggests that he's alcoholic. And so this goes in the top left quadrant here. Leonardo DiCaprio is not particularly elderly, but there's a drink there, so it's up there. The most interesting man in the world does have a bottle of Dos Equis in front of him. And he's a bit older than Leonardo DiCaprio, so we can plot these things out. Point is we can plot all these images out. Here we got some kids. Here we got some elderly folks. We got Bernie Sanders once again asking you to give him beer money. And we have Grandma discovers the internet. And so they're all kind of, you can plot these out in this very simplified two-dimensional space. And then to see how similar they are, rather than just kind of looking at the numbers, you can do fairly simple geometry. The easiest one to use is Euclidean distance. You literally draw a line between the 2 points, and whichever line is shortest, well, that one's the closest. And so if I upload a picture of someone with Leonardo DiCaprio, I would probably find my closest match would be the most interesting man in the world. You can also do cosine similarity. And so cosine similarity, what it does is it measures the angle from origin to the point, to the 2 points, and wherever the angle is the shortest, they're the most similar. And so this finds things that are more similar using a different mechanic. Cosine similarity probably gives you the best results, just because of how embeddings work. The magnitude tends not to be quite as important as the direction. And you can also do range queries where you can say find a point here and say give me everything that's within a certain distance of this, if anything. And so there's lots of interesting ways that you can compare these vectors to each other, these embeddings to each other. So that's what an embedding is. It's this, but with more dimensions. With these images, I believe the image embedder I'm using creates 512 dimensions. And so you've got a very hyperdimensional space, vector space that these can live in. And so that is actually quite, you can encode a lot of points in something like that. So a vector database then is a database that uses these embeddings, that uses these vectors. I'll use those words interchangeably. Where you take a bunch of vectors, you take a bunch of images or text or whatever you want to create embeddings on, run them through the models, get your pile of numbers, and then you load that pile of numbers along with other data into a vector database with that embedding and those numbers. Obviously, I work for Redis, so I think Redis is the best option to use here, and so that's why I'm going to use them on all my demos. But there are many to choose from. So here we've added Success Kid and perhaps the image itself and the embedding. We've got the most interesting man in the world, the image itself and the embedding, and mocking SpongeBob, the title of it, the image itself and the embedding. And so these are all loaded into a database. And then you can do this process I described earlier of finding the Euclidean distance or doing a range query or finding the cosine similarity or doing the inner product between the two vectors and finding out which ones are the most similar, and then query it just like you would any other database. But now you're querying on these vectors which have encoded meaning, and so you can find things that are similar. We're going to use this at our demo at the end to take a picture of myself. I can't really take a picture of anyone in the audience easily, I don't think, and find out which meme character I most closely resemble. And so I've loaded a bunch of memes into a database into Redis using this technique, and we can then take a photo and then compare. Vector databases, of course, need to index this so that they perform. There's two ways of indexing that are popular. They're not the only two ways, but they're the two ways that most tools are supporting. There's flat, and there's hierarchical navigable small world, HNSW. Hierarchical navigable small world. Easy for me to say. Flat is kind of what you think it is. It is a brute force search. It is, I mean, there's an index there, but it is literally just comparing every vector. Like it's going through every vector until it gets the match and finding the best match. And so it's literally an O of N operation over that index. It's got perfect accuracy, but of course we'll run into scaling limitations. On Redis, I'm told the number, and obviously this could vary greatly, is around 1 million records. You need to start caring about this, which is still a lot, but that's where you need to start caring. So there's flat. Then there's hierarchical navigable small world, and this creates sort of a subgraph at the top, and then more fully fleshed out graphs as you go down through the layers. And the idea is that you find the nearest node in the graph, the nearest node to you, that matches semantically, that using whatever distance metric you're using. And then from there, you'll go down to the next layer in the graph and find nodes that are next to that are closer to what you want, and then the next layer, and you sort of hone in on it. And this gives you approximate accuracy, but you can control how many nodes are connected and how dense the different layers are and how many layers you have, and that can just give you different variations of speed and accuracy and space. So you've got several levers you can control there. So when you start scaling up, this is a popular option. a vector database doing searching with embeddings like this can be used to do a fair number of interesting solve a fair number of interesting use cases. I'm going to talk about 3 of them here. The first one is semantic search. This is what we're going to demo tonight. Semantic search is that simple case where we have a database full of embeddings and their associated data. So here we have 3 embeddings of text. I don't have the little embedding icon in here, or a little pile of numbers, but it's there. So deletion is 100% file compression, first meme. TypeScript is just JavaScript for C# devs. Changed my mind. I stand by this. Everyone's going TypeScript. I still love JavaScript more, even though I'm complying. And code doesn't compile, compiles again. And so you've got this database here, and there's presumably many more things in here. And then we take something that's similar. We want to find a similar meme. Don't need to debug your code if it doesn't compile. We run this through an embedding model, which turns it into a pile of numbers. And then we go in and match those numbers using the flat index or the hypernavigable small world, and using either cosine similarity or Euclidean distance or whatever distance metric we want to use. And so this is your basic semantic search use case. Find things that are like this other thing. Give me the 5 closest things to the thing that I gave you. Very powerful, can find all sorts of things that you could not find more easily using structured search and structured data. The next one is semantic caching. So semantic caching, I think, is a particularly cool use case, particularly for Redis, since it's well known as a cache. The idea here is that LLMs are expensive, and users tend to ask the same question over and over again of them. And so you could hit an LLM every single time a user asks a question, and then have the LLM generate a response and then get your response. But if a few users come in and ask what is effectively the same question, it would be nice if you could cache on the intention of that question as opposed to the exact phraseology of that question. So here we've got grandma discovering the internet. She's learning about dank memes. And she wants to know, can you explain to me what a dank meme is? And we got an LLM who is prepared to answer this question. But what we do is we have answers to previous answers from the LLM cached in a vector database, along with an embedding of the question that was used to generate it. And so when we say, can you explain to me what a dank meme is? You can go and find similar answers. What is dankness? I don't understand what memes are. These aren't quite exactly what grandma's looking for. And so we're going to create an embedding of grandma's question. We're going to hit the cache. If we get a hit, then we get something that's similar. We do a range query to find out how close it is. If we get something similar, then we return it. And we haven't called the LLM, and we've saved buku bucks. If we don't get a response, we don't find anything, then we go ahead and ask the LLM the question, can you explain to me what a dank meme is? The LLM will return that to the user and then cache it. And now the next time someone comes in and asks a similar question, like instead of, can you explain to me what a dank meme is? Can you tell me what dank memes are? That's the same question, just worded differently. That will match semantically, and then you'll get the cache result. So this is a great way to save money with your LLMs. The last scenario here is retrieval augmented generation. People have been talking about this a lot. This was all the hype last year. RAG, as it's called, is the idea where you can retrieve data about the question you're going to ask an LLM that it might not know. So like an LLM doesn't know my customer's information, or it might not know my product documentation because it's proprietary and it's in-house and it wasn't on the internet. It wasn't part of its training set, or, and so you can retrieve extra information and hand that to the LLM along with your question. This does not have to be done with semantic search of any variety. You don't have to use a vector database to do this, but it can be very useful to do so. You could actually just do a straight up, pull it out of SQL, pull all my customer data out and give it to the LLM and say, here's my customer record. And can you, should I contact them about, renewing their auto insurance warranty or their car warranty? So here we have, again, grandma saying, can you explain to me what a dank meme is? This particular LLM, for some reason, was not trained on internet data and has no idea about memes or dankness or any of that. And so it needs help. And so we take grandma's question, we create an embedding, we go to our vector database and find matching embedding and text to go with it, documentation explaining this thing. And then we hand that context, that text to the LLM. Say, given the following context, given all this documentation about dank memes, answer this user's question. And then the answer is then returned to the user. And that is RAG in a nutshell. RAG actually works really nicely with semantic caching. So you can bypass the entire RAG process by returning a cached result as well. So that's actually pretty cool as well. So that's sort of what a vector database is, what an embedding is, and what you can use vector databases for. I want to get into the third topic here, which is talking a little bit about how you can make your own models to create your own embeddings. And I want to put a big caveat on this. And I said it earlier, but I'm going to say it again. You probably shouldn't be making your own models to create your own embeddings. There's lots of really good ones out there already. You can just use them. It's faster, it's easier, and you're probably going to get better results. I'm not a data scientist. None of y'all are data scientists. And data scientists know lots of things about building these models that we don't, and it'll look like it works until it doesn't. And so there's danger in here. That said, this is a great way to learn. And so I recommend exploring this on your own. And I have a talk about building your own models, not specifically embedding models, but on convolutional neural networks. And you can use a convolutional neural network to get an embedding model. This is one way to do it. It's not the main way that we're doing it these days. We're using vision transformers now instead of convolutional neural networks. But I understand how CNNs work, and I don't really know how vision transformers work. And so we're going to talk about CNNs. And furthermore, we're just going to talk a little bit about how neural networks work in general to understand the CNN. And the goal here is not that you can go out and learn how a CNN works and code it up yourself necessarily, or that you really get all this stuff, but it's that you understand some part of it, that you learn that it's knowable. I've got this great book. It's somewhere back there in my office here that I bought from when my kids were younger, called Dangerous Things You Should Let Your Kids Do. Highly recommended if you're a parent. It's things like climb a tree, sit on the roof, play with fire, use a pocket knife, things like this that you should let your kids do, because if you don't let them be exposed to dangerous things, they don't really learn how to handle themselves around things in the world that are dangerous when they encounter them. And it's a little fun at the same time because there's a little bit of risk, right? But there's one thing in there that really stuck out at me was take things apart. And they talk about in the book about a dishwasher. And so, the author took a dishwasher apart with his son. And what happened when his son took the dishwasher apart wasn't that he learned how a dishwasher worked, because he was like 6, and dishwashers are fairly complicated machines. But he did look at how some of it worked, and he understood how parts of it worked. Like, oh, the water comes in here, and this is the little clicky mechanism that controls it, and this is a switch that connects the wires. And so what the kid learned in this process is that the dishwasher is knowable. So that's what I'm trying to do when I go and talk about neural networks here and about convolutional neural networks. The goal is not that you leave this talk being an expert on convolutional neural networks. The goal here is that it's knowable and you learn a few pieces about how it works. So that's the intention here. So I'm going to give this warning on don't do this in production one more time before we get to the demo. So I really want to drive that point home. So this is your basic neural network. You've probably seen a diagram like this before. This is not new stuff at all. This was actually developed. Some of the stuff was developed. I first learned about these sorts of networks in the late 80s, early 90s. But the idea here is you've got this neural network, and it's got a series of layers. And the input layer is where you put in a bunch of numbers. X0 through X3 in this picture are floating point numbers, maybe 32-bit floats or 16-bit floats. And you send these numbers in, and these are numbers that represent your data. And then those numbers are flow out of this neuron to the next layer of neurons through hidden layers. And the numbers are changed as they go along, and they progress the whole way. So, for example, the number that's here in X0 goes to all the neurons in here, and X1 goes to all the neurons. And then the output of each of these neurons goes to all the neurons in the next layer. until you get an output layer, which is your Y. And so it takes numbers in and it processes them, and then it spits numbers out. It's like a big function that takes 4 parameters and returns 3 in this particular example. And it's made of these neurons. So let's take a look inside of what's in a neuron, because these things can be trained and can do surprising things. Your basic neuron has an input. This is like the simplest possible neuron ever. Has a single input. This is for teaching. Obviously, a single input neuron is not very useful. You have an input and you have an output. So a number comes in, number comes out. And so this could very easily be graphed because you've got an X and a Y. And so you could draw this on a chart. We all did this in algebra class when we were in school. Inside of the neuron, we have a weight, which is multiplied times the input. We have a bias, which is added to that calculation, and then that generates the output. So simplest neuron you could ever see. You got the input times the weight plus the bias, giving you the output. And if you're astute, you might recognize this formula from algebra class as a variation of y equals mx plus b, where m is the slope and b is the y-intercept. So m changes the angle back and forth like this, and then the y-intercept b slides back and forth like this along the horizontal axis. And so what this means is that a neuron is just a function that draws a straight line. That's all it is. Now, a real neuron has multiple inputs and it draws a straight line in more dimensions, but it's doing the same fundamental thing. But there's a problem with this, which is that straight lines, if you feed them into functions that generate straight lines, that feed them into functions that generate straight lines, that feed them into functions that generate straight lines, you're going to get a straight line. And not all of the problems, not all the outputs of a neural network are straight lines. Some problems that you want to solve are weird and curvy. They draw all sorts of interestingly shaped lines, perhaps shaped lines that there aren't convenient formulas for. And so to solve this problem, data scientists very cleverly said, well, let's modify the value before we spit it out of the neuron. And so they created an activation function to transform this value, to scale it in different ways. They tried a few, but kind of just landed on using one. So you've got a sigmoid, which basically approaches 1 and approaches 0. So it takes that number from negative whatever, negative infinity to positive infinity, and smashes it down and creates you a nice little continuous thing where 0 is 0.5, and then negative numbers approach 0, and positive numbers approach 1. You got hyperbolic tangent, which is pretty much the same thing, but it's tall and it goes from -1 to +1. And most commonly used is ReLU, rectified linear units, the most overly named mathematical function that I've ever seen, because it really is just max x comma 0. That's all it does. But all it does is say if it's negative, get rid of it. It's just 0. Otherwise, leave it alone. And this tends to work the best. I mentioned already, this is more realistic neurons have multiple inputs. This is still not a realistic neuron because it only has 3. But the math is basically the same. It's the input times the weight plus the input times the weight plus the input times the weight plus, for all the inputs, plus the bias yields the other number, and then that's run through an activation function. And then, so here is the mathiest slide we have here. It's the summation of the inputs times the weights plus the bias. So this is sort of neural networks 101 in maybe 5 or 10 minutes here. And if you can build these fully connected neural networks, you can do some very useful things with them. But convolutional neural networks are particularly interesting because they are really good at pulling apart images and vision. And here's a diagram of one. You've got an input layer here at the beginning. This input is literally the pixels of the image that have been adjusted to be numeric. So, 0 through 1 as opposed to 0 to 255 for the RGB. And generally, actually, there tends to be multiple layers, one for the red channel, one for the green, one for the blue, and maybe one for the alpha channel. But we're going to do a simple black and white with just the pixels. And then this input is run through a series of filters, and these filters go through a chunk of it at a time, where they're mapped to each like 2x2 area of this input is mapped to each filter. And the filters are sort of like pattern matchers and saying, does this 2x2 section of the input image match this pattern, yes or no? If it does, then it gets marked in the output. And if it doesn't get marked in the output. You end up with a map of where those patterns are matched. And then you can then feed this into another filter and more outputs. And so what happens is the first filter is finding lines and stuff like that go different directions. And then the next, and you're getting a map then of where all the lines that go diagonally from the top left to the bottom right are, or that go horizontally across, et cetera. And then you take those maps and feed them into other filters that are looking for patterns of diagonal and horizontal lines. And then it finds shapes. And then you take those maps of shapes and so here's all the triangles and here's all the circles and here's all the squares. And then you're like, okay, well, this is, and it keeps building up this thing until you have faces and cars and all sorts of things. During that process, you'll have a pooling layer occasionally. This sort of compacts it down a little bit so that the outputs, if there's any noise in the output, it's sort of averaged out. And then at the very end, you can flatten all these pooling layers out and you get a bunch of values. These normally are then, if you're doing image classification, fed into another layer, a fully connected network, which will then classify it and say that picture contains a cat, that one contains a dog, that one contains a ball of yarn, this one contains grandma discovers the internet, this one contains success kid, all those sorts of things. But the flattened output actually here is the features that we talked about earlier in the embedding. So one of these outputs in here represents perhaps the alcoholicness of the image, and another one might represent the elderliness of the image, and then a bunch of other things here. And so this flattened layer actually is an embedding. A little bit of better vision here of how these filters work. So here we have my attempt to draw a troll face in pixel art. It kind of succeeds. And then here I've got various filters with horizontal lines and a vertical line on the right and a corner and that kind of stuff. And I'm going through here and I'm looking in this image to find patterns and mapping them out here. And I've got a little animation to kind of drive this home. So here we're scanning across it. So we're going through and does this match? No. We're trying to match that filter. And then as we match the filter, where the filter is two dots, one in the center and one on the right, then we map that out to the output. This one doesn't, this one doesn't, this one does, etc. And so we end up with this map of where the filter, this pattern is in the input image. And this is a little bit of a simplification because these aren't actually, Boolean values. This isn't pixels on, pixels off. These are numbers. And so these would not be numbers from 0 to 1. It would probably be numbers from 0. They would be numbers from 0 to 1, but they wouldn't all be 0 or all 1 because it'd be grayscale. And then the filter is numbers as well. And then the output is numbers as well. And so some things match more hardly than others. So like these twos here represent a strong match of the eyes. But because this is a horizontal line, it kind of matches the top, the bottom, and the mouth. And so you can kind of see it's found almost complete horizontal lines. And these numbers, as it turns out, are part of the formula that I mentioned earlier. So all these inputs here, these are the X's. And then we take those inputs times the weight, sum them up, add a bias, and then run them through ReLU and map them to our output. And so this is doing that same calculation that any other neural network could do, but it's using it to find patterns in an image. Pooling is actually much easier. You can basically take a different pattern and you can say, is a thing in there or not, and then compact it down. And so this is a way of sort of compressing it down. And this, again, is also numbers here. And you can kind of see, there we go, how these numbers correspond to it's looking at this little 2x2 square and says there's a 1 here, so I'm going to take the max number in that 2x2. In this 2x2, I'm going to take the max number, etc. You can do max, you can do mean, you can do, there's many options here. And then we get several pooling layers at the end, and we get all this pooling layer at the end, and we can then map, we just flatten it out. We literally just take the first row and it goes here, and the next row is here, and the next row is here, and the next row is here. And so we just flatten it out. And again, these are also numbers. So far, so good. Everyone's brain full yet? There's a lot of detail in a very short amount of time. So that's how this flattened out value here is the embedding. And so we could take these numbers and then we could use them because what's basically happening is this value here says, I found an eyeball and I found a cat nose and I found all the various features of the images that are identified in these pooling layers get represented in these flattened values in these numbers. And if the numbers are big, it's got that feature, and the numbers are small, it doesn't. So that's embedding models very quickly. So once again, devs, you should totally check out the custom embedding models and play with these. It's a great way to live your life. This meme is a terrible way to live your life, but from a developer point of view, go out there, play with these, and learn about them. But when it comes time to go to production, do not create your own embedding models. Data scientists are the people that you want to work with if you have a need for them, and oftentimes you don't. One does not simply create their own embedding models. This actually, he's saying a lidless eye wreathed in flame, but yeah. So don't just go out and create an embedding model on your own and roll into production and expect to have a good time. You're not going to have a good time. It'll look like it'll work, and then it won't. And honestly, you should be working with your data scientists, because the data scientists, if you've ever tried to operationalize some of the stuff they've done, they need the software development expertise that you've accumulated over your career just as much as you need their data science expertise. And so there is a very synergistic relationship there. So that is the warning a third time. So let's go on to the demo. Just call out Chappelle here. He got mentioned twice. He got two different memes in the slide deck. So I've got a demo that I'm going to show you that uses vector databases to find your meme twin. I am not saying I'm going to use Redis to do it, but I'm going to use Redis. And hopefully, with luck, I will match this guy because it's hysterical. So here's what I've built. I've built a thing. And that thing consists of Redis as my vector database of choice. And then I've wrote a piece of JavaScript code called a meme loader. It's just a project. It's just some TypeScript code, actually. What the meme loader does is when it runs, it creates an index in Redis so that Redis is able to then do a vector search on these image embeddings. It then reads a directory full of meme characters, which are all out in GitHub, creates embeddings for each one of those, and then writes the embedding and the title of the meme and the bytes of the meme, the actual image itself, all to Redis so that it can be searched and retrieved. And then the meat of the application here is this client and server. The client just takes your photo and sends it over the wire. And the server then takes that photo, creates an embedding using the same model, uses that embedding to search and match, saying, give me, find the top one most similar embedding to the embedding I've given you, and then fetches the image and the title and sends it back down the wire and puts it on the screen for you to see. So this is basic semantic search. So let's try out the demo here. Me when I see a talk, but before the demo. So we're going to see how my camera works with. Okay, I gotta get this out of slideshow mode. Can I? No. There we go. Hey, that's working. Can you see my screen?
Yes.
Perfect. Okay. So I'm going to look to the left here because the screen that I'm sharing is actually on the left here, and my presenter view's here, and my camera's over here. So I'm not ignoring you. So this is the code. We're not going to look at the code yet. I am going to go ahead and just run this. Docker compose up. Actually, let's take a look at the code first. Let's make everyone have to work for the juice. So the interesting this is actually really easy. This is the thing that I think is kind of fun about this. So this is my meme loader, and this is really the important thing. So this is creating a bunch of indices and Redis and stuff, and this is kind of boilerplatey code that you probably should just look at on your own when you pull this repo down yourself. But the main thing it's doing is it's creating the indices, and then setting up all the indices so it's searchable. In here in main, I'm literally looking at a folder, and this is all in TypeScript. So I get a directory. I make sure that I get only things that end with PNG or JPEG. That way I don't get the directories and stuff. And then I just loop over the files. And then I call a little embed function, which we'll see in a moment. And then I right here, inject that into Redis. So I get the title, and there's the key, and I set the title, which is just the file name, the image, which is the bytes of that file, and the embedding, which is what I got from this embed function. I just set those in Redis. And so this is all it is literally just tearing through things in a folder and adding them to Redis. The embedder, which is where the magic happens, is right here. And so this code, let me do that, is surprisingly short. I'm using a library called Hugging Face Transformers, and I'm importing a function called pipeline. What pipeline does is it's a function that creates a pipeline. It does a thing where it tokenizes and it does the convolution, all the things that are needed. Does the transformation of the image, so make sure the image is the right size, and then slices it into its layers, and then turns it from 0 to 255 to 0 to 1, and does all that pre-processing, and then feeds it into the neural network, and then spits out an embedding. And a pipeline does all that for us with one function call, so we don't have to write any of that code ourselves. And so here I'm saying, create me a pipeline worthy of Mordor. It is for image feature extraction, or it could be feature extraction for text feature extraction, or one-shot classification, or there's lots of options in here. I'm going to use this model here, Zenova Clip Vit Base Patch 32. This means it does little 32 by 32 pixel patches in the image calculations. This is a vision input transformer, and it also does text as well. So you can do text to create embeddings and images to create embeddings that are similar. So you can do image search by saying, show me a meme of an old man drinking a Dos Equis, and then it would do that. This doesn't work very well in Node, but it works great in Python. But the model I'm using supports both of those modes. And then over here on the right, I'm just telling that it is using 32-bit floats. So this call to pipeline builds me a function that I can call that will do all the things in the pipeline. I'm calling it the extractor. In here, my embed function takes a string to the path to the image. And so this pipeline even will download the image or load it from a file or download it from a URL. You can even give it a data URL. So it doesn't even have to be a real file on the internet. But you give it that URL, and then you pass it into the extractor, and it returns a tensor. That tensor has your embedding in it under the data property, which is a float 32 array, which I extract. And then because I'm using Node, I need to take that raw data, that float 32 array, and get the buffer of bytes. And then I need to turn that byte array back into a Node buffer so that I can hand it to Redis, because Node Redis operates on Node buffers because it's a Node application. And then but regardless, that gives me my embedding, and I return it, and that's it. That's all that it takes to make an embedding. When you go to actually do a search, let's take a look here. You sort of reverse, you kind of do the same thing again. This embedder here is doing, it's the same code. Like, it didn't even change when I clicked on it. And the matcher, all it's doing is it's building up a query against Redis where we're saying match everything and then filter them by k nearest neighbors. I want the top one where my embedding field, which is a field in Redis, matches this blob, which is the embedding that I'm passing in. And it builds this query where in parentheses, you have sort of a conventional search. And then the little arrow function with the square brackets here then has the vector query. And so, and we could go into a lot of detail, but the reality of it is you won't remember any of this code. It's all out on GitHub, so you can go play with it. But the key things I wanted you to see here is that this is sort of how you build your query right here to talk to Redis, and that the embedding using Hugging Face Transformers is really it's not much code at all. And it will even run in a web browser, which is particularly cool. So, got that. Now, let's go ahead and kick this off. Let's Docker compose up it. Yes, I'll allow it. Okay, now what's happening right now is it's downloading the model from Hugging Face, but once it's downloaded it, when I run it again, it'll be cached, and I won't need to go do it. So I need to stall for a few seconds while it downloads the model. These models can be rather large. I could take the model and download it myself and put it in the repository, but I just haven't been bothered to do it yet. Okay, so here it's loaded all the images, right? So we got everything from Afraid to Ask Andy to Zombie Boy. So it's all loaded. Perfect. Let's try it out. This is the part where it fails. Yes, I have a super awesome homepage. Okay, localhost 5,000. I think it's 5,000. Nope. 8,000. There we go. Allow. Let's see. It does work. It's oddly formed, but this should be fine. So I wasn't sure if this was going to work or not. It is worth noting that I got all tall, didn't I? So, okay, let's go ahead and use this and see if we can make it work. We're going to take my photo. I'm going to get up close here. God, that's horrible. That's horrific. And let's see what. Yeah, you're a wizard, Harry. Yeah. And here I am, American Chopper. Yeah. So I can actually change the distance metric that I use, so from cosine similarity to inner product to Euclidean. I'm going to change it to Euclidean and try it again. And we won't get quite so crazy this time. It won't matter. If I use that, yeah, it's still the same. Let's try inner product. It picks up on the background as well. So I found that if I'm in a lighter room, generally Paul Sr. comes up, and if I'm in a darker room, the most interesting man in the world comes up, which is quite flattering. And when I do inner product, it tends to do really random stuff. Oh, wait. Try this again. I've selected inner product. Use. There we go. Hide the pain, Harold. Lots of times it'll come up as mocking SpongeBob, but you'll notice that it picked up two things fairly consistently in all these images. I'm a middle-aged white guy. And it matched me with, for the most part, middle-aged white guys. The most interesting man in the world is ostensibly, I guess he's Hispanic, isn't he? I mean, he's drinking Dos Equis, so that's a thing. But I mean, he's fairly pale skinned. He's got gray hair, and he's got a beard. They all have beards or some sort of facial hair. So it's picked up on middle-aged, light skin tone, white hair on their face, and it's matched all these things. I don't know that I could. Let's see if I can do something interesting here to try and get something else. So I'm gonna be dangerous and bring up a photo on my phone and see if I can get something fun to match here. Let's see here. I don't have very many photos of people on my phone. Here we go. Let's do this. There we go. Oh, it's not going to focus. Let me adjust the focus here. It's great. Okay, take photo. Go back to cosine similarity, hit use. Well, that's interesting. It picked up, normally that does Grumpy Cat. But it picked up, I'll get myself back in focus here. There we go. It picked up on the fact that it was animated. It's like it's got bright colors and stuff like that. So normally this is the part where I have people come up and try it out for themselves. But because we're virtual, I can't do that very easily. But what we can do, hang on, I'm still kind of out of focus here. There, I think that's better. But it is out there on GitHub, and you literally saw me type Docker compose up. You can clone the repo. You can do Docker compose up, and it will work. I ran this on my old MacBook that was Intel based without the Apple hardware, and it still worked just fine. So it'll work on pretty much any computer that you want to throw it at. It might even work on a Raspberry Pi, but that might be living a little bit dangerously. So that's the demo. Code's out there for you to go play with. Please do. And in fact, here's the QR code that will take you to that code. You can go to this repo, clone it down, Docker compose up, and try it yourselves. I probably should have had Richard set this up ahead of time so he could demo it for everyone else. That would have been smart and required forethought, but alas, We're not too late for that. But go out there, scan this QR code. If you're curious about Redis and want to learn more, you can go to redis.io and learn about Redis. We have courses, free courses, university.redis.io, many of which I've recorded. And we have a Discord server where you can go out and ask your questions. I'm the main admin there that manages it. So go check out our Discord server. And to go ahead and scan this QR code. You can totally trust it. It will never give you up, nor will it let you down. And got one last thing here. And I can throw the link in chat too, actually. I can try to anyhow. There's one last thing here. This is a shout out if you want to, want to give Redis a try as your vector database because you need some sort of vector semantic search solution. This is the results of a benchmark we did about a year ago. There's a blog post that this QR code will take you to, and this is showing this throughput speedup factor is a multiplication of the database in question versus the one that scored lowest. So like here on Deep Image 96 Analyzer. Or Angular, sorry. Redis was 53.23 times faster than the slowest one, which looks like it was MongoDB Atlas. And so, and you can go out now. I mean, it's a benchmark, right? So take it with a little bit of a grain of salt. But the benchmark code is out there. You can run it yourself and tweak it and experiment if you need to do some performance measurements. So go check that out as well. That's pretty much all I've got. I can take questions if there are any, but yeah, thanks a lot. I'll put the QR code up here still. Any questions? I can't see hands up, so if there are, just shout them out.
I was dazzled and amazed, so I had questions.
Dazzled and amazed is a good way to be. Cool. Well, then I'll stop sharing. And
anything online?
I'm not seeing anyone. A couple people left the chat, so they must not have any questions. Cool. Well, I'm going to stop sharing then. I'll get my I'll get that QR code in there post haste. Let me bring my browser up. I need to pin that as one of my top repos. So here it is. There's the repo in chat if you are virtual, or I don't know if you can access it. I'm still not in focus. I think that's better. I've got it set to manual focus because reasons. I'm working on video recording, and in order to get it to do the thing that I want, if I leave it on automatic focus, it constantly, the lights behind me will flicker in and out. The autofocus kind of does this, and it's really annoying. So I had to turn it off and just do it manually.
What are those lights in the background?
It's just LED strip lights. I've got a remote for them right here, so I can like make them. I don't know if I can. It's always hard to get to.
Definitely makes for a great effect.
There, see, now they're green, right?
Nice. We got looks like we got one question in the chat.
How much does this cost to run for a day? Well, I mean, that's a complicated question, obviously, because it's going to depend on a lot of things. But the running that I'm doing is free. This is all the stuff. It's all running locally. The Redis instance is Docker running locally, and the model has been downloaded from Hugging Face, and the code is running all locally on my machine. So if you want to play with this, it's free. In terms of cost, I don't have a good answer to the cost question for using it in Redis specifically. It's Redis databases are generally sold based on how much data you store. And so you could go out and get like a free tier, which is like 30 megs, and play with that. And there's lower tiers that they start at like dollars a month and scale up to as much as you want to spend. But for something fairly basic, you could spend, you know, like a fixed tier, maybe $20 a month and do plenty. It's not particularly expensive, and you don't even need to use that because as developers, right? We're mostly just wanting to play with these things and use them locally. And in fact, that's actually something I didn't talk about in my talk that I like to talk about is like I've got 3 things that I'm trying to prove with a lot of this AI stuff. One is that it doesn't have to be Python. JavaScript's viable, and lots of other languages have tooling to do this. I'm just not as familiar with them. So it doesn't have to be Python. It doesn't have to be online. You can run it locally. I've been using Olama on my new MacBook, which is admittedly fairly beefy. I got an M3 with like 38 gigs of RAM or something. And I can run like DeepSeek on it, and it's very performant. And so this stuff can run locally. It does not need to be in the cloud, and so you can be disconnected. And third, you don't have to flop out a credit card to pay for any of this stuff. You can, as developers, you can use all of this for free. And so I think these are actually really important aspects for the developer who's learning, but not necessarily getting to do the stuff at work yet. Now, that said, I've done a lot of stuff with OpenAI's stuff, and I put $20 in my account, and I think I've spent like 10 cents since January. And so it's not super expensive, even when you're using the remote compute. So yeah, this is very accessible is I guess the point. And part of the reason why I like to do stuff locally is because I have a lot of I've done a lot of talks at events. And when you're doing a talk at an event, you don't want to count on the Wi-Fi at the conference. Yeah. And so anything, if you can do everything locally, that is the safest way to do it. And so I tend to favor it for that reason too. So I see a green light blinking. Oh, okay, it's good. Never mind. So any other questions?
We're all good. Thanks again. Really appreciate it, guy.
Absolutely.
And thanks everyone online. I hope to see you in a couple weeks. All right, I'm gonna go ahead and end the meeting.
Catch you
Good night,
later.
everyone. Take care.